everyone, my name is Salazar. I'm a neuroscience graduate student here at the UC Davis, and the title of my talk is FastBrain, Can Specially Designed Video Games Improve Cognitive Function in Children with 22q? So recent research over the past decades has shown that children with 22q have spatial and temporal impairments that they face from an early age. We have seen that children with 22q have trouble with attention, spatial cognition, and quantitative cognition. At the root of all this, we hypothesized that a reduced resolution of attention may be causing these impairments. If you look at these two pictures on the screen, you might be able to notice that the picture on the left is a lot clearer than the picture on the right. This is because the picture on the left is considered of high resolution, which means it contains many pixels, than the picture on the right, which is considered a low resolution picture containing fewer pixels. So in kids with 22q, mental representations of space and time have a low resolution or fewer pixels. Targeting and treating these cognitive systems from an early stage can improve the overall quality of life in children and adults with 22q later in life. So to recap, kids with 22q face spatial and temporal impairments from an early age. Basically what this means is that the difference between two items needs to be bigger before they can tell the difference between them. This leads to difficulty with numbers, math, and navigation as they grow older. One of the main effects of spatial and temporal impairments in kids with 22q is a pronounced crowding effect. Crowding refers to the inability to identify objects when they're in a clutter. I'm going to show you guys a demonstration now so you guys can get the idea of what crowding really means. When I show the next picture, there will be a cross on the left here, and then there will be lines on the right. I want you guys to look at the cross and try to count how many lines there are on the right, if you can. So again, look at this cross here on the left, and then as you're looking at the cross, try to count how many lines there are on the right. So many of you, while you were doing the activity, probably thought you saw 2 or 3 or 4 lines on the right, but there's actually 5 lines. And this is in essence what the crowding effect really is. The lines on the right are cluttered, and so while you're looking at the cross on the left here, you might not be able to tell exactly how many lines there are on the right. We all experience crowding, but kids with 22q exhibit a pronounced crowding effect. Here I'm using a real-life image of what crowding can also look like. So if you're looking here at this red line right here, and you try to count or try to identify how many kids are crossing the street. I'll give you guys a second to try and do that. Many of you might be able to notice this kid on the right here, on the bottom right, but a lot of you probably didn't catch this kid on the bottom left. So this is because the kid on the bottom left is being crowded or cluttered by the street signs. And when you're not looking straight at it, you're probably missing it due to the crowding effect. Crowding goes hand in hand with a system called the useful field of view. The useful field of view refers to the area from which an observer can extract information with a quick glance. So if you look at these two circles that are overimposed over the image now, the red circle represents a person with a normal useful field of view, and the yellow dotted circle represents a person with a reduced useful field of view. A person with a normal useful field of view has a larger area where they can extract high resolution visual information from. And in this case, they might be able to detect one or both of the children crossing the street due to their increased area from which they can extract information. In contrast, a person with a reduced useful field of view, which is the yellow line, might not be able to detect one or either of the kids crossing the street. That's because due to the reduced area, the area where the kids are outside of the scope of which they can extract high resolution visual information. And this goes hand in hand with crowding, because having a lower area from which you can extract high resolution of visual information can heighten the crowding effect. So what can we do to alleviate these spatial temporal impairments as it relates to crowding and the use of field of view? So recently, research has shown that action video games have had selective benefits in spatial attention, spatial resolution, and temporal resolution. If you guys notice, these benefits are the same systems that are impaired in kids with 22q. So using this knowledge and the findings from the past 20 years and 22q research, Tony's company, Cognivive, has developed a prototype for a neurotherapeutic video game designed to improve spatial and temporal processing by targeting the systems involved in crowding and useful field of view. FastBrain, as the name is right now, but it might change later, has two different modes. One of them is the useful field of view mode, which is designed to improve the useful field of view of the player. It does this by using a thematic storyline where the player has to collect gems that are appearing on the screen with the help of robot minions. So as you can tell here from the video, the gems are appearing around the circle, and the gems are appearing in one of 8 directions: up, down, left, right, and the diagonals. And the player just has to flick the direction with the joystick where the gems are appearing. Over time, the gems are appearing further and further away and at faster rates. FastBrain also has what we call the crowding mode. This mode is designed to improve or focus on reducing the crowding effect of the player. In this mode, if you can see here at the very top, the player has to collect energy in order to power up a robot that will go collect gems. So you do this by pressing a button to the rhythm that the gems are going through the green line. And once you have enough power to collect enough power to get the robot, an arrow will appear somewhere in front of the minigame, and you have to click the direction the arrow is pointing to. So as time goes on, the minigame here can change position from being at the top of the screen, the bottom of the screen, any of the quadrants of the screen. And the arrows start appearing more cluttered and further away. So we've designed a study to test the efficacy of FastBrain on kids with 22q. This was funded by the UC Davis Business Incubator Grant. And the design of the study is described here in this table. So basically, we had participants come to the Mind Institute on 3 different occasions. The first time was baseline testing. We wanted to see where they were at in our tasks prior to playing anything or doing any training. Then they played either FastBrain or Tetris for 4 weeks. Came back a second time, did the same task again to see where they were at. And then switched games and came back a third time and for tasks again, and then they were done. So the reason why we chose Tetris as the other game they would play is because Tetris served as our control video game. So for those that are not familiar with Tetris, Tetris is a simple old arcade game that requires manipulation of blocks as they fall from the top of the screen to the bottom of the screen. And the point of the game is to make rows at the bottom of the screen. So the reason why I chose Tetris is because Tetris requires spatial manipulation of only one object at a time, in contrast to FastBrain and other action video games that require spatial manipulation, distributed spatial manipulation or attention, where you have to look at the whole screen and be paying attention to the whole screen at the same time, and not just at one object at a time. So we wanted to see what the effects of playing Tetris versus the effects of playing FastBrain were on the tasks that the participants did on every visit of the study. One of the tasks that we used was a spread of attention task. This tested for useful field of view. And this task was pretty simple. So what we asked the participant to do was look at pictures of what we called raindrops. This one is one of them, and this one is one of them. And after they saw 2 pictures of raindrops, we asked them to identify which of the 2 pictures of raindrops contained a patch of raindrops going the wrong way. So if you look over here, this picture, the second picture in this sequence, contained the patch going the wrong way. The patches could be either near the center of the screen, which is considered to be 15 degrees of visual angle from the center, or they could be near the edges of the screen, which is considered to be 30 degrees of visual angle from the center. So here we see the results from this task from 8 kids that participated in our study. On the x-axis here, we have the error rate, and on the y-axis we have the error rate. On the x-axis we have the eccentricity, or the two conditions that I just mentioned, 15 and 30 degrees. So the blue represents the baseline, which is the first testing date that when the kids arrived. The red represents the Tetris effect, or by how much Tetris reduced error rates after playing Tetris, and then in this task. And then the green represents the FastBrain effect, which is how much FastBrain reduced error rates after training. So as you guys can see, the highest are the baseline testing error rates, and then Tetris had a small effect here, and also in the 30 degrees, and then FastBrain had the biggest effect of both games in reducing error rates. What this suggests is that FastBrain training improved the useful field of view of our participants. Another task that we used tested for the crowding effect, and this is called the Cambridge crowding cards. These cards are a well-known and reliable measure of visual acuity and crowded acuity. So the way this task worked is I would stand about 3 meters away from the participant, showing them 2 sets of cards. The first one only had 1 letter, and they just shouted out which letter they saw. And then the second one was a clutter of letters, and they were supposed to shout out the letter in the center. So if you guys have ever been to the eye doctor and look at a chart like this and have been told to say the letters, you probably were told by the end of your visit that you have either 20/20 vision or 20/30 vision. So what this means is that at 20/20 vision, you can see what a person with normal vision can see when they're 20 feet away. If you have 20/30 vision, at 30 feet, you can see what a normal person. At 20 feet, you can see what a normal person can see at 30 feet. So you need to be 10 feet closer to see the same thing. And this is what these cards are measuring. They're measuring they're measuring what you can see compared to a person with normal vision, and that's what we measured. So here I'm showing the results for the crowding cards, the cards that were cluttered. On the left, we see the crowding ratio. On the y-axis, the crowding ratio, and on the x-axis, the participant. As you can see, if you look at participant 1, this was the baseline crowding ratio. Tetris didn't change for any of the participants after playing Tetris. The crowding ratio didn't change. And then for FastBrain, 4 out of the 7 participants that we had in our study showed improvements in crowding after FastBrain training. One other thing we wanted to look at was, can FastBrain training change brain function? In our lab, we have ways to measure brain activity. And one of them is by putting an electrocap in your head and measuring the brain waves as you do a task or activity. We wanted to see if FastBrain can change the way the brain processes different images. So what we did was we had a simple task where the participant looked at these checkerboard patterns, and there were 4 different conditions: single, close, medium, and far. In the single, there were only 2 checkerboards on either side of the screen. And in the close, medium, and far, there were 4 checkerboards separated by increasing degrees of visual angle. So close was separated by 1 degree of the visual angle, medium by 2 degrees, and far by 7 degrees. Since FastBrain is expected, or we thought it would improve crowding, we didn't expect any changes in brain processing after FastBrain in the single and far conditions, because these conditions are not crowded at all. But we did expect some changes after playing FastBrain in the close and medium condition, since both of these conditions are cluttered by the checkerboard patterns. So what we see here is the results of 1 participant that completed this task, and at the point of this talk, this participant has not finished Tetris, so this is just FastBrain here and baseline here and FastBrain and the green. And we don't see any differences for the single, close, and far condition, but we do see a difference in the power that the brain elicited to looking at the medium condition after FastBrain training. The reason we maybe not be seeing anything in the close condition is because they're so close together that they're too crowded even after training that there might not be any difference. So overall, what these results show is that there might be some processing changes occurring in the brain after FastBrain training. So in conclusion, we see some behavioral and brain processing effects after FastBrain training, as seen in the crowding and useful field of view, as seen with the tasks that measure crowding and useful field of view. We see processable range changes in the tasks that I just mentioned with the checkerboard. And it seems that we are on the right track with treatment. We just have to find ways to optimize it and improve its efficacy. So what is Cognivive doing now? So one of the things moving forward for Cognivive is to implement the game into a virtual reality platform. This allows the game to add a third and fourth dimension, incorporate head and body movements, and optimize different algorithms that will help improve the efficacy of the treatment. Another thing that's very important for kids is to make the game more engaging and entertaining. They will have to want to play the game for it to actually work. Finally, we hope to get do more testing, more participants, more brain scans. The more the better. The more participants we have, the more data we have, and the more we can see the effects of training, of FastBrain training. Finally, I want to thank the kids who participated and the family who participated in the study. Our lab members who helped early on test the prototypes and tasks, 2 philanthropic donations who helped fund this study as well, Ted Aronson who worked with Tony in creating the game itself, and the UC Davis Office of Research Venture Catalyst Group.